Yes. So, good morning to everyone. I welcome all of you to the 23rd lecture in the lecture series in Nonlinear Dynamics, conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Professor Sudeshna Sinha from ISET Mohali. Professor Sudeshna is a well-known name in nonlinear dynamics community, not only in India, but also around the globe. Professor Sudeshna's contribution to the field can be easily understood upon looking at her awards. She started bagging the awards even from her school days. For example, the Scholarship Award NTSC in her school days, Best Outgoing Student in the Master's Degree Program from IIT Kanpur. These two awards when she was a student. For her research, she won the following awards: Birla Prize for Physics, J.C. Bose National Fellowship. I want to mention that Birla Prize is being awarded to Indian scientists below the age of 40 years who have made outstanding original contributions to their fields. Besides this, Professor Sudeshna is a fellow of all three Academy of Sciences and also Third World Academy of Sciences. Professor Sinha works on several areas in nonlinear dynamics. To name a few, I spell out, she works in chaos theory, complex systems, network computations, and currently on machine learning. She serves as an editor for a couple of international journals and acting as an editorial board member in a couple of Indian journals of physics. She completed MSc in IIT Kanpur and PhD from TIFR, Mumbai, and worked several years in the Institute of Mathematical Sciences, Chennai, before moving to ISET Mohali. I think she is serving as a deputy director of that institute right now. Professor Sudeshna visited our department few times already. Few months ago, I had attended one of her online lectures, which she was delivering at Mumbai University. I noticed that the talk will also be useful to our MSc students. So I requested her to deliver the same talk in this forum so that the MSc students will get benefited. Professor Sudeshna has kindly agreed to do the same. Thank you very much, Professor. With this short introduction now, I hand over the session to Professor Sudeshna Sinha. Over to you, Professor.
Thank you. Thank you very much for those generous words. So let me maybe start by presenting my slides. So I should, of course, have to confess that this is, this is the 23rd talk. So probably the audience is very mature. And of course, I see renowned experts in the audience. So I will apologize to them for being a bit elementary, at least to begin with. But I do hope there will be enough in the audience who can take something back from it. Okay, so I'll let me share my slides. I do hope you can hear me, right?
Yes.
Okay, great. Okay, can you also see me, or am I visible as a speaker? Okay, good. Okay, because sometimes I can't quite see it on my screen. Right. Okay. So what I thought I would do today is start with a very quick and shallow introduction to some key concepts of modeling complex systems. And essentially what I want to draw your attention to are surprises that you can get in such systems, which come from the interplay of order and disorder, the local dynamics, and the global organizing principles of connectivity. So these are, sometimes they work together, sometimes they work against each other, and the balance of these conflicting trends give very counterintuitive phenomena. Okay, so I just hope to indicate a few illustrative examples. But before I get to the meat of it, let me say a few general words. This will go on for like 15 minutes. So again, apologies to experts and for the mature students in the audience. So when I start these lectures, I really want to emphasize that we are looking at classical phenomena. And, the word classical mechanics is often used as, a polite word to say very old. Okay. And in some sense, to twist a quote of Eugene Wigner, the unreasonable effectiveness of classical mechanics is one of the most amazing things. It is It appeals to mathematicians because it's mathematically rigorous, and it's also an extremely useful toolkit. So it's also very applicable. It's also something which engineers use on a daily basis to understand phenomena, and what they understand, they use. Okay, and it holds for an extraordinarily large range of scales. So, my colleagues in labs which do nanomechanical oscillators also use them on a daily basis, as do my astrophysics colleagues who look at phenomena at an absolutely different end of the spectrum of scales. So both in time and space. Now, you could think of the concept of chaos as a new frontier in classical mechanics. So it's like a new kid in a very old block. And it has, in a nutshell, caused us to reassess the way in which we view the classical physical world. So a few general words. So one of the eternal quests is to foresee the future. I mean, that's how astrologers make money, right? So one of the beautiful things about classical physics is that it is deterministic. So if you know all the properties of a system, in principle, by system you can mean anything from a particle in a box to a weather patterns of the earth with Avogadro number of particles, whatever. If you know the laws of physics, then you can perfectly predict the future. This is a kind of expectation from such systems. And this is what we mean by a clockwork universe. Okay. But the surprise was this, that a large range of simple natural processes could exhibit enormously complex behavior. So complex that it appeared as if they were evolving under random force rather than a deterministic law. So basically, to paraphrase it again, some completely deterministic systems displayed exponential sensitivity and were in effect or essentially unpredictable. You did not expect to see these two contradictory things said in the same sentence. Determinism giving you this clockwork universe picture of the universe, and unpredictably giving you this thing which is essentially moved around by random forces. So this necessitated a paradigm shift in classical systems, and which led to this emergence of this new science, or new mathematics maybe, of chaos theory. And I like to show this slide, though it is just general and a little bit of light entertainment. The word chaos actually has been used in common usage in all languages, in all forms. So, for instance, one of the earlier ones I have seen is written as so in Greek letters, refers to an abyss in Greek cosmology. So, in some sense, it is the emptiness or pre-order, before things came into being, before order. So not order, pre-order. And there is apparently a Chinese symbol for this, which I learned on one of my visits to China, which I hope I've got right, which looks like so, which also essentially stands for this concept of chaos. And if you look at the English dictionary, like a Webster, a Merriam-Webster, the word chaos might show up as confused, unorganized, disorderly state. We use it freely, to describe everything from traffic to politics to, everything is used very, very often by this colloquial word. But as a technical term, it appeared in scientific literature for the first time around 1975, one would think, in a paper by Lee and York, an American Mathematical Monthly, which said period 3 implies chaos, where, it has a very specific technical meaning. So just to go on the little bit of history, does God play dice is what I titled these couple of slides. Now, the first hint that nature can be both deterministic and unpredictable goes back to the 1800s, actually. So there, the King of Sweden, like a prize, offered a competition where anyone who could solve the so-called three-body problem, gets something. So prizes for sciences have been old, as you can see from this. Now, French mathematician Poincaré won the prize without actually solving the problem, a kind of mathematician thing to do. Instead of solving it, he wrote about the problem, describing all the reasons why it couldn't be solved. So he drew attention to the problem and its enormity. So one of the important reasons he highlighted was that small differences in the beginning of the system could lead to big differences at the end. So perturbation theory was in danger. Okay, so another way of saying it is the present determines the future. That's the nature of determinism. But importantly, approximate present does not approximately determine the future. This is the issue which one has to kind of keep in mind. And things kept rolling, and people serendipitously sort of hit upon the idea while doing computer simulations. So this came much later and did not even come from the physics table or the maths table, but from an atmospheric scientist. And so he was studying a simple model. And you know what people do when you run a simulation, you stop it, and then you restart the simulation, you keep your values, and then you put that in as initial condition, you go have tea or lunch, and you come back and start it. But when he did that, he got wildly different results. So what he found was this surprising sensitivity to initial conditions. So the tiniest rounding of error, which you don't even think about when you do simulation, 1 part in a million. So at the 64th decimal place, or in binary, say, or 32 if your machine is not so good, would lead to a completely different behavior in the model. So essentially kind of discovered chaos without using those words. Now, why do we bother? I mean, should we even be worried about it? Now, the reason we have to be worried about it is it's widespread in nature. So for instance, Newton's laws from your coursework, you do classical mechanics, everyone does it. It's the workhorse of all physics courses. So when you do it, you know that the thing which will come in the exam are the ones which allows precise analytic formulation. And for instance, you would have done simple pendulum, you would have done the two-body problem. So these allow precise analytic formulation. Even though you may not have done the simple pendulum with elliptic functions, you would have at least done it as a simple harmonic oscillator approximation. But one seemingly small increase in complexity leads to chaos. So we really have to worry about it. You can't just say, oh, this is very complex, so we don't have to worry about it. We'll stick to our simple end of things. You can't, because you add one more thing and all bets are off. So you do your simple pendulum with one bob, you go and add a second bob. And you have complexity which you cannot describe unless you stick to very, very small part of your dynamical possibilities, namely, very small angle approximations. The three-body problem, same thing, which actually stumped even great mathematicians like Poincaré. So here is a picture which you've seen in Wikipedia probably, and I'll just keep it for 1 minute. And this is a long exposure of the double pendulum. And just to tell you that this is not something which will come in the exam, because it is really hard to solve. Okay, so something which looks like this will emerge if you don't stick to very small approximation. This is tracked by a LED and a real, very real system and a very simple system. That's what I'm saying. So typically, this whole branch of deterministic chaos is also explored, not just in the mathematical framework, in departments of mathematics, but also what are called maybe experimental math or applied math or numerical experiments or simulations. And of course, they're also done through laboratory experiments, as I know my colleague have given wonderful lectures to you already on the kind of experiments that are possible. Circuits, I'm most definitely sure Professor Murali has done. Probably some on chemical systems, fluids, lasers have also been touched upon. Okay. So just to put a number on how simple can you get before you worry about it. So a dynamical system, let me put it out there now, is a deterministic mathematical prescription for evolving the state of the system forward in time. Flows, which we say could be described in the continuous time framework, would be given by bunches of differential equations. And maps, which are discrete time, which I will have illustrative examples of soon, are given by iterated functions, which look like so. So there your time is a discrete counter. It's an integer, which is like a clock, which goes at the back. Okay? You can think of it like a stroboscopic system. You see the state, you wait, see the state again. Do remember, almost all experiments are actually maps, because whatever is your sampling rate, you're actually sampling in discrete time. All numerical simulations are also maps, because you are actually, whether it's the Euler method or the Runge-Kutta, you're actually implementing a map inside your system. So it's actually a very broad framework. And X is the point in your n-dimensional phase space where the action happens. And so from some initial state, you can in principle solve these equations and obtain the future of the system, which I will call an orbit or a trajectory or a flow. Question is, how large does the system have to be in order to exhibit chaos? So for n first order autonomous ordinary differential equations, n greater than or equal to 3 is sufficient for chaos. Just need 3 coupled ordinary differential equations, such as the Lorentz system or the Rossler system, and you can see it. As you can see, the pendulum is actually 4, because it has 2 angles and 2 partner momenta, and so it's a 4-dimensional system, so definitely falls in this class. For maps, if an inverse exists, so if it's an invertible map, and if the inverse is unique, you can get chaos even for 2-dimensional systems. So basically, you can have X in a, say, for instance, defined in a plane, XY, and if you have a map which maps the state XY to another state XY, such a map, if it is invertible, you can get chaos. But it gets simpler than that. If the map is non-invertible, you can get chaos for n greater than 1. So n equal to 1 is can also give chaos. And which is why most of your simple examples you have done in coursework starts with 1D maps, because it's the simplest thing which is capable of displaying chaos. So here is a 1-dimensional, non-linear, discrete time map, the logistic map here, the binary shift map, which is 2x mod 1, which is 2 straight lines. So it's piecewise linear, which is also non-linear. The tent map, which is also piecewise linear, 2 straight lines, okay, 2 which look like that. Binary shift map looks like 2 straight lines like that. And this is a standard thing which you'll get in a 10-second run of simulating these things. So if I didn't tell you, it came from such a simple deterministic equation ticking like clockwork in the background, you would have looked at this extremely messy, extremely complex thing and say, my God, maybe I was just tossing random numbers and getting it. And indeed, if I'd gone to my laptop and written a program where I just draw random numbers and shown you a series, you would have not known the difference to the eye. Okay, so something so complicated came from something so simple. And the underlying thing here is the stretch operation, which takes neighboring initial states and pushes them exponentially fast apart, and the fold operation, which pulls it back to the interval and keeps it bounded. So you want boundedness, which comes from fold operation, which also gives you non-invertibility, and the stretch operation gives you the positively upper Lyapunov exponent. And here is one last picture on this. I like it because it's the Arnold's cat map. And I like it also because everyone thinks only quantum mechanics has cats, but we have, you know, nice mangled cats as well. So here is this poor cat's image in this box, 0, 1, 0, 1 box in X. This is X, this is Y. And all I've done is to take this mapping, 2x plus y mod 1 and x plus y mod 1, giving x and y at the next iterate. Very simple. If you look at it, linear things, but mod 1 gives you the piecewise linear part. And this is what it does in one iterate. It stretches and then it folds back into the box, which keeps it bounded. That's the mod operation. And in one step, this particular image is unrecognizably mangled. So it's unrecognizable that this thing could have been that poor cat. So this is the enormous effect of some very simple set of equations that you can do. So we have to worry about it. It is not some esoteric thing which happens when lots and lots of things are getting together. Okay, so it is something which is extremely prevalent. Okay, and so the question, of course, I've just listed some, is how do simple laws give rise to such intricate structures? Why is it ubiquitous in the physical world? Of course, because it's simple. That's why it's there. If you had these complex, almost random looking things, does it actually still embody some simple patterns, which could be, written as universal scale invariant laws? So is there some order embedded in this disordered, complicated looking thing? So you're going from simple things, order, to disorder, back to order. So you're trying to look at disordered systems and trying to again go back to it and say, is there some pattern there which I can, which pops out to the eye? And of course, the eternal question, whatever you're seeing in the lab, is it random or deterministic chaos? And last one is, it is a truly interdisciplinary enterprise. Okay, so there is no way in which this field would have progressed the way it has unless it had involved people from very different fields, from atmospheric physics to bio to chem to of course physics and math. So this whole thing was actually to draw attention to the phenomena of the whole being more than a sum of parts. So now I want to say that, okay, I told you simple things give complex stuff. But what if counterintuitively, when you put together complex stuff, you get a whole which might begin to look simple again? And or there are patterns there which are, broad and neat. So the Nobel Prize of Physics was in fact awarded for groundbreaking contributions to our understanding of complex systems. So half the prize was to Manabe and Hasselmann for physical modeling of the Earth's climate. So you can see it is a physics prize which has gone to something in a different discipline, which tells you how this complex system discipline is interdisciplinary, even at the highest levels. And of course, to Giorgio Parisi, who I would say is more statistical mechanics, but essentially this interplay of disorder and fluctuation at all scales is what gave it, in some sense. So a couple of quick slides before I'll give you a few illustrative examples from my own work, but general things are things which I think stay with you longer. So I will not cut corners there. So let me give you a few more minutes on another idea. So let me now come to the idea, okay, of how can I mathematically model a complex system, okay? So a model, as I said, would be considered a good model if it is a simplified mathematical representation of the system, okay? Don't worry about putting everything in, okay? That is not a model. That is like an analog of it. A model actually takes the key features which you think are important. So your taste in what you think are important comes in there. You take the key features, which is thought to play an essential role in what you have observed or what you found interesting. So some of the art in this is to find the key features in building the model, okay? And so here is a little cartoon which I love to show. This is the essence of scientific modeling according to Picasso. So this is a Picasso picture. This is a real thing. And you can go through steps to sort of capture the essence of this very complicated thing in this picture. And when you see it, it actually evokes the full object. And if you make a good model, it should do that. So of course, why do we do it? Why are people employed to do it? Why are people making careers out of it? You want to explain data. That's the first thing. Experimentalists are producing data. So you want, especially in bio, and in earth sciences, so you want to explain data. And as Eugene Wigner said, which I had misquoted or twisted his quote in the beginning, is the unreasonable effectiveness of mathematics to explain data. We must keep it in mind. We are always in business if your understanding of the basic mathematics is good. And what we want to do is to link together levels or hierarchies of explanation. So basically the large aggregates, you have to understand, is not understood by the simple extrapolation of the behavior of constituents. If you could do that, you could understand everything by reducing everything to a simple harmonic oscillator, say, and just build it up. You can't, because if you take aggregates of simple things also, it could behave in ways which are counterintuitive, which we call emergent in some ways. So the models would integrate our understanding from one level to another. So we want to provide simple rules from which everything else is derived. So, and you want to find out the consequences which arise from your model. So you propose a model. Where does the model take you? What are the full mathematical and numerical consequences of your model? And of course, this will help you rationalize what behavior you have observed, and hopefully next plausible future outcomes can be done. And remember, it could be in broad strokes. So qualitative modeling is a very valid exercise. So elementary identities of science at one level obeys the laws of science at that level. So if you start at the most foundational level, our colleagues who do high energy physics or are engaged in atomic and molecular physics would say, you have elementary particle physics, you should be able to say something about atomic and molecular physics, from where you should be able to do many body physics. From many body physics, you should be able to do chemistry. You keep going. From chemistry, you should be able to do biology. From biology, you should be doing physiology, maybe psychology, maybe from psychology, you should do social sciences and economics. So there is this hierarchy, a flow which you think should happen. And it might seem that everything that is happening at the higher emergent level is uniquely determined by physics operating beneath them. But this hierarchy does not imply that X, the science that you're doing at X, just applied science at level Y. Okay, it is not the case. Okay, so more is different. This is the thing, which was Anderson's great motto, which caught on a lot, because he was actually struggling against so much of physics being dominated by elementary particle physics. So at each stage, entirely new laws and entirely new concepts may be necessary. So complex systems as a discipline attempts a more precise definition or description of these. It is made out of large number of interactive components. For instance, individuals in a population, species in an ecosystem, buyers and sellers in a market. And it is not, if it's just a sum of parts. So if I took hundreds and hundreds of simple harmonic oscillators which are not coupled, it is not complex because it reduces back to the parts with no extra emergence. So in order to be complex, it can't just be a sum of parts. It must do something interesting, show behavior, which is more than a sum of parts. Okay, so as I said, more is different. And how do you study it? You build models. So there's a whole range actually you can do, from simple, which is almost like a cartoon, to complicated and detailed. And there is a balance. So simple and conceptual versus detailed and realistic. So there's a trade-off. So you could, of course, say, consider a spherical cow in vacuum in zero gravity. And then, of course, you can take a particular cow, brown cow with 6 spots or whatever. So detailed and realistic may be necessary for a very specific purpose, but most of us engage with simple and conceptual. So the trade-off is broad understanding from simple conceptual models, which teach us how broadly things work, and quantitative predictions, which you may need for very specific situations where, of course, specialized models, which are almost like copies of the real thing. So these are the two ends of the spectrum. Most researchers do both things. Both are useful in the context. Increasing level of abstraction gives broad understanding. In increasing levels of description, you get more quantitative predictions. You have to balance. And there are two basic approaches. One is top-down. You essentially break down a system to gain insight. So that would be by analysis, decomposition, reductionism. So each system is refined in greater and greater and greater detail. So you look at the big thing and you keep going down, okay? And you might even need additional subsystems till the entire specification is reduced to base elements. Right? This is more elementary particle physics approach. Bottoms up, which is what the next last half of it will be talking about, is the bottoms up approach. You piece together systems to give a grander system. Okay, so the original systems are subsystems of an emergent system. And these are linked together to form larger systems. So the links matter as much as the subsystems. Okay, and so the strategy is to have a seed model, say a chaotic map, and then build from it a spatiotemporal model, which is a linked set of coupled maps. So this would be like a standard sort of approach in this business. So from beginnings are small, but they grow in complexity and completeness. I would call it the synthesis approach. Okay, and the recipes are so basically, what do you want at the end? Large, strongly interactive systems, or what often are called extended systems in introductions of such papers. So you need local dynamics, typically low dimensional systems which you understand, or maybe even in your coursework, and you add to it connections, that is links. So you link them. These will, there you need to specify the topology of the links, the coupling forms, and whether the links themselves have dynamics or not. So there could be dynamics at local level, there could be dynamics on links. So all of this is essentially broken in these parts. And there are three things which you have to take care of. The space, because it's extended system, could be spatiotemporal. Space is in a very general sense. It could be a network where space is just a vertex. But in some sense, space, time, of course, dynamics, so no escape from time, and state variable, because that is what you are interested in. That is the physical variable of interest. You have to follow something in space and time, and that hopefully may be an experimentally observed quantity as well. It could be a temperature, pressure, velocity, concentration, population density, charge density, what have you. And the hierarchy of models which one builds looks like so with this scheme. Class of models, I've put discretization in space, time, and state variables. If all of these are continuous, at the head of the pyramid are partial differential equations. And I'm sure you've heard talks on many PDEs already. Okay, so this is, everything is continuous. Then you start discretizing them. It actually helps also to understand, because the base elements get simpler. So it could be that you're making your space or your entities discrete. Then you may have oscillator chains or oscillators on networks. Here, space is discrete. That's an integer. There's a finite number of them. Time is continuous. State variable is continuous. So you have ordinary differential equations, but distributed like this. The third thing is space is discrete, time is discrete, and state variable is continuous. So these are coupled map lattices, for instance. That is to say, you have a bunch of maps of the kind I did in the first 10 minutes, strung together. So time is discrete because it's a map. So it's an iterated function where, time goes like an integer counter. State variable, some x, y, some real value function. And you keep iterating it. So this is in this class. And there are at the bottom of the pyramid, very, very powerful method called cellular automators. And everything is discrete here. Space, time, and state variables. That is to say, there is a discrete set, a finite set of variables which describe your state. Okay, so what in the illustrative examples in the next 20-25 minutes, I will have examples from coupled map lattices, oscillator chains, and cellular automata. I will go through it very loosely without too many details. Okay, so what will I try? I will have linked local chaos on a complex network. So that is to say, the links could be very non-trivial. And what question will I ask? The question I'm going to ask is, what is the spatiotemporal behavior of a collection of elemental chaotic units with varying degrees of randomness in their connection? I will also ask, these questions will make sense a little later, does switching the underlying connectivity influence these patterns? So what would that mean? It means there's dynamics on the network and dynamics off the network as well. And how does this interplay of the nodal dynamics, the local chaos, and the change of links, which is also a dynamics of its own, how do they interplay with each other and what comes? So is it one simple answer would be you have local chaos, you put in more randomness, you get more randomness. But is that the answer, or do we actually have emergent order from this disorder? And what I will show you in the next whatever time I have, 25 minutes as far as I can tell, is that I will show you that random links can suppress local chaos and induce global spatiotemporal order. So it's from order to disorder to back to order by putting extra disorder. So dynamical connections, I will also show, can mitigate another very problematic thing which can happen in your models, which is a blow up. So these are unbounded growth. I mean, my students had come saying, oh my God, we have put nice van der Pol oscillators. Nobody has had problems, but everything is blowing up. And then we found that if we put random links in this network, it actually suppressed blowups. It tamed the blowups. So I'll have a few examples. So both of this is example of disorder giving order. Okay, and I will suggest that maybe such mechanisms of putting disorder in the links, actually suppressing the disorder at the local levels, may be a mechanism by which natural systems actually control themselves in a natural way. So specifically, consider a ring of coupled nonlinear maps. The word sites, which could also be interchangeably be called nodes or vertices, are actually denoted by integers, discrete space, as I said, 1 to some n, could be very large. I will call it a lattice or a network, depending on whether there are random links or absolutely regular lattice structure. On this is a state variable, which is real, which I call x1. There's just one state variable at each site. So they are going to be 1D maps. And this is your variable of interest. So take one of these. Here is the on-site part. Okay, this is the local part. F of x sees only I. Okay, but this bit here is your nearest neighbor interaction. So it also sees things which are outside its local domain. So there's a local part plus coupling, which is your standard modeling framework. Okay, and let's take, for simplicity, as I had shown you in that very complicated fully chaotic logistic map which I showed, let me throw the full chaotic logistic map at the on-site. So it's locally completely chaotic. So these are two pictures. Even if you forget the rest of the talk, I just want you to retain these two pictures. Picture one. This is a bifurcation diagram. At each spot in your coupling strength, I'm putting points for the value of x ni, which I get in time, okay, for all the sites. And yeah, this is for regular nearest neighbor connections. It looks like a mess. If you have perceived it to be a mess, you're right. It is, in fact, there is, it's spatiotemporal chaos or chaotic bands or noisy cycles. No order. Now I consider the same system, but with its coupling connections rewired randomly. So I'm now putting in randomness, okay, more disorder in some sense. I say that I connect fraction p of randomly chosen sites to two random neighbors, okay. So I replace nearest neighbor by random connections. P equal to 0, this probability is 0. So it's usual ring of nearest neighbor interactions. P equal to 1, it's a completely random network. So this picture you would have seen from many other people. So this is the thing, P equal to 0, regular ring, which I had shown you, but with two neighbors. This is somewhere in the middle, very dilute number of connections, maybe 0.1 fraction. So just 1 in 10 links are doing this. And this is where everything has some probability of going to a random site. Okay, so this definitely looks more disordered than that in terms of connectivity. But what actually came was, and of course you can do this in two ways. You can switch the links, so that's even more, you can take the random links and they're different at different times. Can't get more random than that. Or you can have quenched links. You fix it once and for all, and that's also a way of doing it. Okay, now let me consider dynamically rewired connections. So at every point, my network sees some set of random connections. And if I do this, this is what I get. This is strongly chaotic logistic map with dynamically changing random connections. So my network is changing and giving me different random connections at every point in time. So it looks as if I have thrown a lot of disorder into links now. And of course, there was strong chaos to begin with at the local level. So local level chaos was there, plus disorder of links, somehow together gave, if you just look at this, extreme order. So I got a spatiotemporal fixed point by actually from strong local disorder by disordered connections. Okay, so a spatiotemporal fixed point gains stability when I actually increased the probability of random connections. And in fact, for completely random coupling, I got the largest stable range of spatiotemporal fixed point, which some people might also call synchronized fixed point, but essentially everything goes to the same number in this thing. And so all sites got stabilized. So you have stabilized the strongly unstable fixed point of the local map by giving it these random connections. That was the surprise. So that is what I was trying to say, that just because you understood local chaos and you put in some disorder even in the links, doesn't mean that the emergent phenomena will not hold surprises. In fact, it might hold huge surprises. For instance, this is what I said, even if you forget everything, those two pictures I would like you to keep in mind, where random connections suddenly pulled together everything and made it regular. So one can actually do a lot of analysis with it. So in my old paper, I had done a mean field version of it by putting an average probabilistic rule just to understand, like, where is it coming from? And I could do a linear stability analysis on this probabilistic mean field version of the equation. And by having a few assumptions, one managed to get this particular expression for the onset of the spatiotemporal order. And you can clearly see that, so epsilon equal to 1 is the end of the coupling range, because that is the maximum coupling strength you can have. So if epsilon star is 1, it means you have got nothing. If epsilon star is lower, it means you have got a big range. Okay, so P large would mean lower epsilon star, which would larger range. Okay, so the range is 1 minus epsilon star, and so this goes as P1 plus P in the exact analysis. And if you take P to be much smaller, so dilute random links, it goes as P, as you can see from standard expansion. So basically, it linearly increases the range. So it is really working for you, random links. So regular nearest neighbor coupling gives null range. Fully random connections give stable range. And these are things from numerical analysis. So as I said, everything comes hand in hand. Do some analysis, do some numerics, and it should tie up together. So the dotted lines are from numerics over many lattice sizes. You have to be careful. All of you might be doing these things. Be careful to check for system size, for asymptotics, etc., etc. And it matched very nicely, both with the analysis, which is the solid line, and the numerics. That is how people go about this. It also showed, the first question people ask, okay, you saw it for logistic map. Now, what about circle maps? What about tent maps? What about a map maybe which is showing robust chaos? So the whole thing is that you should check the generality of what you get over different things. And indeed, it holds for all these maps. In fact, as you can see here, these are simulations from all these. You can't even tell the difference because they've fallen on each other. And my postdoc at a later stage had also checked for a system which had robust chaos and saw the same thing. One more thing is, okay, that was dynamic rewiring. What did that mean? It meant that I was changing connections. It was seeing random connections, but every time it was seeing a different one. So, maybe I had seen a non-local neighbor there, then I see one other very far away, different random thing, but it kept changing. But you could do it the other way. You could have static rewiring. So in the beginning, I see random neighbors and it's frozen. Okay, is there a difference? So now we are going to flag the thing. Does the dynamics of the network matter? Does it matter that your links change in time? The answer is a big yes in this case. So in this case, this range of spatiotemporal thing dropped, the average range, sampled over 1 million initial states, dropped with n. So which meant very large systems will not show any range. Okay, and so it kept dropping, and in a sense, this is for p equal to 1. So we could also, of course, understand this through linear stability analysis, which was even very, very easy to do. But the thing to take back is this. The regular lattice gave spatiotemporal chaos. In some sense, no order. Disorder plus order gave you disorder in some sense. Static rewiring, so let me go to the third one. Dynamic rewiring, which is switched random links, had disorder at local level plus disorder plus dynamic change gave spatiotemporal fixed point. No order is more ordered than that. And the middle one, which was static rewiring, which was disorder at local level, plus random links, but with no time dependence, again gave spatiotemporal chaos. So it is very important to explore the full range of things that may happen without prejudice from something that has happened at the lower level of the hierarchy. Okay, so the static to dynamic transition is so stark that, of course, the question immediately suggests as to how fast does a network have to rewire? How much dynamics is needed in order to get spatiotemporal order? And this was a thing from one of my older students. And it showed that if you kept doing it very fast, so R equal to 1 is the time period of rewiring. R1 is the most frequent. At every step, you see a bunch of new connections. R equal to 100 means it sees something, holds it for 100 steps, then sees something different. And so there's a sort of, the links persist for some time, then they are rewired. So this persisting links shrunk the range of spatiotemporal fixed point. Here it's much larger if you do it more often. It is smaller when you do it less often. And this is the trade-off. So the range of spatiotemporal fixed points is actually a function of the rewiring probability, which is a space thing, and the frequency of rewiring, which is a time thing. So there is a sort of trade-off between how much you rewire and how often you rewire. So if your space is very, very random, then you might have to rewire less frequently. If your space is very, very dilute, say only 10% of links are there, then you have to rewire much more frequently. So this is data collapsing, what we say, on a curve, which tells you that is the underlying function. Okay, so if the links are static, you get spatiotemporal chaos. If they're random links switched around fast, you get the spatiotemporal fixed point. And bottom line, rapidly switched links enhance regularity. Okay, now 2-3 pictures. You can sit back. I won't give too much details here, but in pictures, I'll give 3 examples from different systems in different classes of that hierarchy of models. First class, oscillator chains. This was done with my colleague in mathematical biology, Shomdatta Sinha, and her student. So we had a ring of coupled cells. And what were we mimicking? A minimal biochemical pathway, which was a 3-step reaction equation. So we had 3 ordinary differential equations at each point in the network. Okay, and this gave rise to lots of different functional dynamics in cellular systems. Okay, and I will not show anything except that we had this particular set of equations, and as you can see that it wasn't simple to analyze because the functions were quite complicated, but this was what was seen to be of a reasonable model of the system, and the diffusion was just through the end product of this, which was Z. So there was a substrate which converted to another substrate. and it is then converted to yet another one mediated by an enzyme, and there were feedback loops, and there were some autocatalytic productions of also, and all of this is summarized in these equations. And this is the picture. As I said, pictures now. So this is P equal to 0. This is the 100 cells. So x-axis gives you the index of the cells, 1 to 100. The y-axis gives you the time. And this map, density map, is giving you what the variable of the end product Z is. And just by looking at it, you can see that this is ordered because each cell is synchronized here. Here, on the other hand, there is some wavy pattern, is not strict order, okay? Neither in space nor in time. So, in fact, here, because it's so amenable to order that even static gave us order, and see how dilute this is, 0.05 fraction, okay, of links were randomized. And in fact, we found that there was a P tending to 0 transition for synchronization here for dynamic rewiring. That is to say that one link, just one link, throw in and it messes up the whole thing. Okay, it puts order in the whole thing. Okay, so just one link is enough to induce order. So randomness inducing order. The second one I thought I'd put is in the class of cellular automatas. So this was done by Vivek, who was a student at that time with me. I had given him the task of looking at infection spreading on a dynamically changing network, but this was modeled. It was a SIRS model, but that is susceptible, infected, refractory, back to susceptible. And this model was defined in the framework of cellular automata, because I thought we should try a different class of models. That's, you try different classes. So this was the third class. This is his result. I mean, he had many results. I put one picture from his paper. So this said, this is fraction of infected nodes. This is the disease, this is the time period. I have scaled it by a disease cycle just to, so that it looks, I can cover a lot of time. And the network rewiring period from the top to the bottom increases. So when R increases, it means the network is rewiring less frequently. So top, it means it's rewiring very often. At the bottom, it is rewiring infrequently. When it rewired frequently, we had this huge synchronized infection pattern. That is to say, there were huge waves of infection. As we know, in COVID days, synchronized infection is a very big issue in healthcare. But this happened if your network was dynamically rewiring. However, if it was static, even if it had some random connections, it did not have these huge outbreaks of disease. Okay, so the central observation was transition to this low quasi-fixed state, analogous to endemic. We hear these words in newspapers now, of course, because of our times we live in. At that point, 2013, I had not even heard of endemic before I had started the problem. But the transition from that to these self-sustained oscillations, which is periodic outbreak of disease, okay, wave 1, wave 2, etc., is engineered now by links which switch more frequently. So dynamics of the network has come in, okay? Not just on the network. On the network is the SIRS cycle. This is how the network itself changes. So disease cycle get more synchronized, which indicate onset of epidemics as the underlying network changes more rapidly. So what matters is not just the topology of connections, not just how many random links there were, but how fast the links change. Okay, so this I also want you to keep. Here again, we get synchronization out of disordered links. There are things you can do on multiplex networks. I will skip all this. And hyper networks, I will also skip all this. And I will just show this slide because I have, I think, 5 or 6 minutes left. So I'll just show a couple more slides. So I wanted to show this one. because it is a set of experiments also done by, and much more recent. So what this also ties up with is the idea that heterogeneity, so in that sense, disorder of sorts, something which is not regularity, irregularity, also might be a mechanism in suppressing chaos. So something which is disorder is actually suppressed by more disorder. That is the key concept I'm trying to run through these examples. So what was shown by us early in some paper in nonlinear dynamics was that the suppression of chaos in an ensemble of chaotic systems was achieved by coupling to one dissimilar external chaotic system. Everything is chaotic, just that it was a different chaotic system. So here was a whole bunch of things which coupled to one thing which was different. And Murali also had done experiments which showed that this was indeed true. So asymmetry, the second thing I want to show, which was, I mean, I just state without showing the picture, is that asymmetry also we found induces suppression of chaos. And this is a bunch of experiments done in Puneet's lab. I'll show one picture in one slide. Maybe I'll show it right away. So here it is. So this is where he was sort of putting on and off, is to switch on asymmetry and switch off asymmetry. And when he does that, you can see when its asymmetry is on, we get this nice, this is a blown up. This last one is, I have blown up the time from 130 to 133. It is absolutely flat. No, or it's like complete order. Everything has been suppressed. Whereas in other parts, you see there is all kinds of features when it's not there. The third thing is that ill-matched time scales in couple systems can also induce oscillation suppression or chaos suppression. So all of these are building up this picture that heterogeneity may be in the links, maybe in the time scales, maybe in the asymmetry of what is coupling to what. So disorder of some kind, irregularity of some kind is inducing order. So it's order to disorder, back to order. Okay. So sometimes I like to call this whole talk order to disorder and back. Okay. So maybe I'll take 3 more minutes and I will end my, whatever I wanted to share with you today. So I'll just take last 3 minutes because I had mentioned it in the beginning. This was done by 2 of my students, Anshul and Vivek, was still a student at that point, together. And this was yet another direction in which dynamic random links helped to bring something which is useful or something which is more ordered or more regular. So this started with the fact that Anshul found in his network of very first, I mean, I thought his program was wrong, but then I did it and we found the same thing, is that he had an oscillator chain with a certain kind of coupling where he was finding blow-ups. So everything was shooting off to infinity, and this was distressing, of course. And so I said, okay, you are sitting on a ring. Why don't you try to rewire it to a random network? Of course, this was, there was some resistance because it felt as if I was asking him to do more random stuff. And so, how would it make it any better? But, we have some intuition from the old stuff. And what was found was that the blow-up was prevented, okay, first. And if you rewired fast, it also led to synchronization. So blow-up was first thing. Whether you did it slow or fast, it managed. And if you did it fast enough, it even synchronized. So that's like bonus order, okay? And here is another example. It's a long paper with many examples, but I thought I'll pick up this one. So this is a Fitz-Nagumo system. This is without rewiring. There were unsynchronized bunch of limit cycle-like things, which on the phase plane looked like this. Now, when I put coupling, what used to happen was, look at this red line here. This is what would happen to those poor neurons. The membrane potential would just shoot off to infinity. It would be unbounded explosive growth in very short time. Can you see how short the time is? Where it's gone, orders of magnitude it would go. So here is what it would look like in the plane. It would go like this and hit the wall. It would go like this and hit the roof. So explosive growth. However, moment you put rewiring, you suppress this enormous growth and kept it within bounds. So here is another ordering principle from rewiring, which is taming of explosive growth. Okay, and the variation of what I called, you have to think of new order parameters to describe, something which is not so common in literature. So we cooked up a boundedness order parameter, and synchronization order parameter is there because everyone has looked at it, but we needed a new one. And we showed that we could have this transition as we increase fraction of links. Okay, and this is not exactly correlated with the sync order parameter. So you could have bounded unsynchronized motion also, but with enough random links, enough frequency of rewiring, you can have both synchronization and boundedness. So this is it was a huge amount of numerics here, because each point in this pixel was scanned over many initial states. And so this is coupling strength, this is fraction of random links. On one side, the link rewiring probability is small. In this side, D, clearly I have stripped a few things from the paper. On D side, the rewiring probability is 0.9, so very high probability of rewiring. Here, infrequently done. So here, of course, the yellow spot is good. So it does suppress, but it does not do it enough. So that zone which is great increases as you rewire more often. Okay, I will skip this. I'll just put the last thing, that the variation of the minimum fraction of random links necessary to get this can be studied very, very rigorously. And you can have a lot of scaling relations here, because you're doing statistical analysis now, and there are some nice scaling laws underlying it as well. Okay, so that's my last slide. I hope I haven't I think I'm absolutely on time. So what I hope I just wanted to convey to you is that you can think of complex systems as large interactive systems, extended systems, spatiotemporal systems, whichever way you want it. You can use hierarchies of models to get at a picture or a description of such phenomena, which is coming only in this context. In my head, one of the simplest ways of thinking of it is linked local chaos gives very powerful set of models in the umbrella of complex systems. And the significant thing here is the interplay between the local stuff, that's nodal dynamics, and the connectivity. Okay, and the connectivity could also have time in it. So, so it is dynamics of the network, on the network, and the interplay of them. And the counterintuitive phenomena, which I wanted to illustrate a little to you, to tell you how complex systems are more than a sum of parts. Okay, the whole could be very different. And so here, what I tried to show was random links can suppress local chaos and induce global spatiotemporal order. And in a very quick last thing, I also tried to show how it can mitigate catastrophic blowups. Okay, so that's it. I'm done. And over to the organizers and the audience. Yes.
Thank you,
Should
Professor.
I stop sharing, or I don't know?
You leave it. Leave it. People might ask.
Should I stop sharing then?
No. Okay. So the forum is open for questions, clarifications.
So,
so this night's a very beautiful talk, really very enjoyable. I have
right. I see one question here. Why is it necessary for n to be more than 3 for chaos? Professor Centelvellen, I see some.
Yes. In the chat box, there is a question.
I somehow can't hear you all. I'm sorry. I had unmuted myself. I couldn't hear anything for the last 2 minutes. Sorry. Please, you'll have to repeat what you all said. I just couldn't. I had kept myself muted.
Yeah, so that's not, can I ask more?
Yes. Yes, please, please, please. I just didn't hear you because I was unmuted. Yes, sorry.
Yeah, it's a very beautiful lecture, really enjoyable. I have a basic point
Right.
that the whole is not the sum of parts. In my opinion, it's essentially because of failure of linear superposition principle.
True. That is definitely a very nice way of looking at it. Absolutely. Yes, I would. Yeah, I haven't put it in. Yeah, I'll probably steal your idea now. Yes, and,
Yeah,
I agree.
because that is the cause of, that is the essence of nonlinearity. And nonlinearity is necessary for all these complexities,
Right.
order and chaos, etc.
Correct. Absolutely.
Yeah, but even in single system, even in a logistic map, you have chaos, but then suddenly you have the onset of order and so on. Okay, so as you increase the parameter, etc.
Right.
So even in simple systems, you suddenly see the transition from disorder to order and so on.
Absolutely.
Yeah, so when you consider a complex network of such systems, yeah, naturally different factors can enter in controlling complexity.
Absolutely.
So the kind of rewiring that you have pointed out is essentially is a very important aspect, and the way in which you do rewiring can play a very crucial role in controlling the complexity, bringing in order, I think. So, but can you give a general prescription for a complex system? Under what circumstances this can be controlled? So whatever you have
I understand.
demonstrated is
Yeah.
typical examples, numerical examples.
Right.
Can you give?
Right. I understand the question. First, I should say that this is actually one of the hardest questions in this entire field. I mean, this nature of question, because in a sense, often exceptions are the rule, as we all know, when we embark in modeling. So umbrella concepts are actually very hard to come by. So, in that sense, which is why all of us, one of the attempts is to do different classes of systems, as many examples as you can. We need that because there is no proof of it, or there is no rigorous mathematical structure which says this will happen in this case and this won't happen in this case. So I don't think that is there in place. I'm not sure how many. So one has to. I mean, so I think in the nature of the field, one sort of has this, exploring classes, and in that class, one uses expressions that if in this class, this seems to be a dominant trend. So like even the linear stability analysis, which of course even we all have to do, and even from my 2002 paper. So even there, it was still for a class of systems. So whether it generalizes, how much it generalizes, one has to kind of go case by case. So so my only feeling is that our intuition gets sharpened by examples. And in this field, illustration is one of the ways to build intuition. And I wish and the mathematical results which we all have somehow are still not completely broad. So for instance, like the stability analysis which I had for him, I could show that it would hold for any f of x for that class, but not a different coupling class. I could show it only for a different local class. So, the limitations of each analysis has to be put very honestly in our work. And so short answer, I don't know the umbrella overriding reach of it. What I can say is it seems to have worked in a very large class. So one should keep an eye open for it. And for each class, you can explain it, but not, I think, not completely. I don't think I can honestly say that I have a very good answer of the
Okay. Okay.
as a universal concept. I wish I could. Yeah.
Thank you. Thank you very much.
Sariga, do you have?
Yeah, I have one question. So, Deshna, very nice talk, of course, as usual.
Yes.
I learned so much about chaos. So, it's a continuation of this Professor Lachman's question. So, you have this master stability functions and this Laplacian analysis. And then when you said that slow and fast dynamics.
You're right.
So, is it not possible, like, to have in terms of this master stability analysis where you can of a structure with class of the system, and then there if you have this you have this fast and slow, so it should not depend upon which dynamics with respect to that scale.
Yeah, so you're absolutely right. So in fact, most of the papers, I didn't show any of the details. Of course, it has the full analysis for those systems. And within that analysis, you can say, like even in my old 2002 one, where of course it was before the words master stability was there, but whatever, it's the same thing. There, as I could say that if f of x, in fact, there actually I could relate it to the class bounded by f prime of x. So which is why all those examples collapsed on the same curve, because I could choose it like that. But what I'm saying is that, so later on, of course, so for changing the rewiring frequency, one could do other kinds of analysis, like averaging it, time average, one of the very standard things to do, etc., etc. But in all of these, you do it with some assumptions of the coupling form, or so either you try to see does it hold for the local dynamics or coupling form. So each one of them is giving a slightly different thing, right? So given a coupling local dynamics, some coupling forms are doing this. Given a coupling form local dynamics, some types of networks are doing this. So it's not, there are 2-3 things, as you're saying, local coupling form plus network. So you have to fix 2 and do 1, fix 2, do 1, and indeed for keeping two things constant, you can definitely give an answer for the class. Each of these papers have that, but all 3 of them together to get the umbrella universality is the one which which I feel is I don't know if it made sense. I mean, so basically 3 things are there, no? So I can do it saying that class of networks, I can get an answer, but given f of x and given g of x.
I was just looking for that. Can one say that when which kind of evolution will work or which kind?
Yeah, right. Yeah, right. So typically fast is always better. That I think held for every example. The question was how fast. That transition point where the frequency at which you're doing it, that was dependent on f and g. So the fact that if you did it fast, that you will induce with that, we were not having any thing. But there was a transition in those things. So if you wanted to get that point of transition, which I tried in the first one, there it worked. But in general, you'll have to do that analysis for that system.
Thank you.
Sorry, I don't know if it.
Tapas, do you want to rise now?
Good afternoon, everyone. Professor Sudeshna Sinha, it was a very nice talk and a lot of take home for me, definitely. And so I was having this almost similar type of question, like your proposition one is that you have some nonlinear system, chaotic system. Now, if we put something, add up something different chaotic system, then it will be suppressed. So almost along the same line of Professor Lakshmanan and Professor Jalan, is there any the way? I just wanted to know that way to or choose that chaotic system, whichever I will be plugging in a particular system. Is there any particular way to choose that? That's what was my question.
Right. Yeah. Absolutely. I mean, so it's the same answer. So right now it is because some of it is a bit more recent, from 2000. So right now it is in the level of exploration and finding illustrative examples. So of course you want to expand the class thing. So how does it work? So I mean, you do it, you do the numerics, you do the linear stability analysis, somebody does an analog experiment, and you think of a new system, and you keep doing it till it fails. So you say, okay, and you feel that, okay, maybe this is an exception. Now, so it's still case by case in some sense. Of course, you can do linear stability analysis. You can do it and you say, okay, in this system, I'm not finding a sensible range of coupling where this is happening. But if you want I mean, when I say universality laws, I want something more general than saying that I can do linear stability analysis from where I can find the answer. Of course, that all of us do. But what is the commonality is what I don't know, because that is going to come from examples, and if I find it, I'll be very happy, because then I'll say something. So right now what I can say is asymmetry does it, heterogeneity of time scales even does it. That was even nicer, because same system, but just so Fitzhugh Nagumo going at a different time scale, which they could do wonderfully in their labs actually, or changing the time scale of the Chua. Just the same system with different time scales was doing it. So heterogeneity was giving order. But, and of course, you can do the linear stability analysis, get the same, you have to cross-check. So the only overriding principle I could find was this, where how strong the coupling has to be, how much asymmetry there has to be, how much free, those are system specific to my knowledge. If someone has a scaling relation for that, I don't know. I have not found it yet. I personally haven't found it yet either. Yeah.
Okay. Thank you very much. Thank you, Professor.
Hello, Senthil Belan.
Yes,
Senthil
yes.
Belan.
Yeah, you can go ahead. Yes.
Sudeshna, I enjoyed your talk. It's a really wonderful talk. Yeah.
Oh, Shamal, I couldn't see your face. Yes, hello.
Now, so it's a wonderful talk. I enjoyed it. You actually presented a very philosophical view of complex systems, and I like the cartoon, especially the cartoon how complex Picasso. It's really wonderful. I enjoyed that. And I must confess one thing now, because you showed order in some spatio-temporal order with the disease model, with rewiring. So in 2020, I published a similar thing in a lattice, but I missed your reference. I didn't cite your reference. We use the same technique. We use the same technique of really using the time scale of rewiring, and that works. So I'm very sorry. I must confess that. The question is now.
I mean,
question is now. So it's a very difficult time. Yeah, there is a disorder in the Baltic Sea. So who will control that disorder? This is just serious.
Yeah. I was going to say, even if I know the answer, I will not give it in public. This is the time not to give any prediction in public. In case it's wrong, somebody will kill me.
But in the scientific forum, we should be part of by this sort of disorder. So it's a real disorder in the society, in the humanity. Okay.
Unfortunately, there is no ordering effect. There's no ordering effect of that disorder, unfortunately. So there's a counterexample of a complex system just getting worse.
Once again, I thank you. Very wonderful lecture. Thank you. Bye.
Thank you.
So there are a couple of questions in the chat box.
Yes. I saw two questions. I can see them. Three is there? I saw one which says, somebody asked, is it more than three or something? I saw. Okay, right. I'll just quickly answer them. So Naveen Bharti has asked, why is it necessary for n? Actually, not more than three, more than equal to 3. So it can be 3 also, 3 and above. Okay. That's the necessary and sufficient condition. So this also comes from another very famous theorem, Poincare-Bendixson, which tells you up to 2, what is possible. And so only where the fact that everything is confined on a plane gives very strong restrictions on what possibly can happen. And so only when you go to 3 dimensions is it a possibility. So please do remember, keeping, for instance, what Professor Lakshmanan also said, this is not sufficient. So there are 3-dimensional equations which are regular, okay? Just like the 1D map, there are regular points, there are chaotic points, okay? So it's not, but it is, so it's necessary, but it's not sufficient, okay? I don't know if you are a bit rigorous in that sense, but all it says that you can find parameter regimes of certain 3D systems which can do it, and this comes from this thing. See, if you think of it intuitively, if your flow was on a line, what could the flow do if it is unique and it exists? Then you can only be a fixed point, or you can run off to infinity, or plus infinity or minus infinity. That is all the dynamics that can happen. If you're on a plane, you could be a fixed point, or you could be a limit cycle. That's a possibility. Only you have to go up to at least 3 in order to have a trajectory which is not confined to be either of these 2 things. And there is a theorem which tells you up to 2 this happens. After 2 you're free from that theorem, Poincare-Bendixson. Okay, that's one. And the other one is, how do you differentiate chaos from spatiotemporal chaos? Yeah, so I've been using the word spatiotemporal chaos to mean, see, after all, oops, I think I should unmute. So one of the things is that you have space and time. So actually all kinds of things can happen. You can have order in space, but disorder in time. You can have disorder in space and disorder in time. So spatiotemporal chaos means that you have disorder both in space and time. So for instance, suppose my ring of cells shows synchronized chaos, happens to many of us in our models. Then in time there is disorder because there is chaos, but in space there is order because there's synchrony. So that is, so in spatiotemporal chaos, there are no correlations either in space, that is not among the different elements of your constituents of your system, nor is there any in time. So that is how you will change. So, okay, I hope I answered that. And the third one is, blow up can be prevented only by faster or slower rewind. So in that, of course, this was done very over huge amount of simulations for all kinds of models of rewiring. And there is, so that was that 2D picture which I'd given with the probability of rewiring and the space in which you get order. Okay, so that is actually, there are some scaling rules there which also can be done, but the quick and slightly not rigorous answer would be faster induces order over a larger range, slower induces order over a smaller range. That's it. So I think I don't see any other questions.
Are
there any more questions? Or
yes, there is one person raised his hand. Prasad, can
yes, ma'am. Thank you, ma'am. It was very nice lecture, ma'am. Ma'am, I have one doubt, ma'am. Very basic doubt. Am I audible, ma'am?
Yes, yes, I can hear you. Huh?
Ma'am, in the, I have doubt in the macroscopic range, in the word, many lot of things seems in very order and systematic. So the pupils also says that since the things are very systematic, so it has to be controlled by someone. So from your lecture, but I was observing that can I conclude that since the things are occurring in the microscopic level are very random, the rewiring is very random in the microscopic level. So the whole the result what comes in the macroscopic range, it used to be in the order. So can I conclude like this?
Yes, I think to qualify it, of course, obviously for classes of systems, etc., all the usual qualification, all of us are, very do carefully. But these are examples definitely of what you say. That is to say, at the microscopic level, there is disorder, and so it's a self-imposed, it's a self-organized sort of order, because you have not imposed it from outside. You have not given external input. In fact, no external inputs are there. They are just talking to each other. They're just interacting with each other. And that somehow has a way of pulling everyone to a steady sort of situation. Yeah, that is the idea in these examples. As I was telling, unfortunate to all our learned members who, of course, have asked the right question. They're bound to be exceptions. There are also bound to be regions in your space where maybe this won't hold. But there are very large number of examples where it seems to hold, both analytically and in numerics and in experiments, which we have set up. That's it. Yeah, but you're sort of right in what you were saying. Yeah.
Okay, ma'am.
Yeah.
Thank you, ma'am. Thank you so much.
Okay.
I think suppose if you have more questions, you can write to her. I think.
Yes, you can definitely write to me. Yeah,
I can suggest.
I have a class in the afternoon also, so maybe
Yes. So
yeah, at some
let's
point.
wind up the session.
Yeah.
Thank you, Professor, for accepting and delivering a very pedagogical talk in this forum, despite of your busy schedule. I believe that our MSc students might have taken something to hope. I will write to you for other details. Okay.
Sure.
Thank you. Thank you very much.
Thank you. Thank you for having me.
Yeah.
Thank you. It's very nice to see all of you virtually. I hope sometime I can come down. Yeah. Okay.
Yeah,
Bye
please,
then. Huh?
please,
Yes. Okay. Thank you for inviting me. Okay. Bye.
Bye.
Bye, Sarika. Bye, Professor Lakshman. And I think maybe Dana is there or not. Okay.
Yeah.
Bye.
And Muruganandam is also there.